Hello everyone, welcome to Center for Future Technology. In this lecture, we are going to start inferential statistics. Descriptive statistics describe data, for example, chart or graph, and inferential statistics allow you to make predictions from that data. With inferential statistics, you take data from samples and make generalization about a population. For example, you might stand in a mall and ask a sample of 100 people if they like shopping at stores. You could make a bar chart of yes or no answers, or you could use your research to reason that around 75 to 80% of the population likes shopping at stores. There are two main reasons of inferential statistics. Estimating parameters. This means taking a statistic from your sample data, for example, the sample mean, and using it to say something about a population parameter, that is the population mean. Hypothesis testing. This is where you can use sample data to answer research questions. For example, you might be interested in knowing if a new cancer drug is effective, or if breakfast helps children perform better in schools. Let's say you have some example data about a potential new cancer drug. You could use descriptive statistics to describe your sample, including sample mean, sample standard deviation, making a bar chart or box plot, describing the shape of the sample probability distribution. Now, inferential statistics, binomial theorem, hypothesis testing, normal distribution, t-distribution, central limit theorem, confidence interval, regression analysis or linear regression, comparison of means. So let's start with binary theorem. The binary theorem is a quick way of explaining a binary expression that has been raised to some power. For instance, the expression 3x minus 2 to the power 10 would be very painful to multiply out by hand. Thankfully, somebody figured out a formula for this expression, and we can plug the binomial 3x minus 2 and the power 10 into that formula to get that expanded form, the formal expression of the binomial theorem. Hypothesis testing. Data alone is not interesting. It is the interpretation of the data that we are really interested in. In statistics, when we wish to start asking questions about the data and interpret the results, we use statistical method that provide a confidence or likelihood about the answers. In general, this class of method is called statistical hypothesis. The term hypothesis may make you think about science, where we investigate a hypothesis. This is along the right track. In statistics, a hypothesis test calculates some quantity under a given assumption. The result of the test allows us to interpret whether the assumption holds or whether the assumption has been violated. Two concrete examples that we will use a lot in machine learning are a test that assumes that data has a normal distribution, a test that assumes that two samples were drawn from the same underlying population distribution. The assumption of a statistical test is called the null hypothesis or hypothesis 0, also known as H0. It is often called the default assumption or the assumption that nothing has changed. A violation of the test's assumption is often called the first hypothesis, hypothesis 1 or H1 in short. H1 is really a shorthand for some other hypothesis. As well we know is that evidence suggests that the H0 can be rejected. Hypothesis 0, that means H0, assumption of the test holds and is felt to be rejected at some level of significance. H1 assumption of the test does not hold and is rejected at some level of significance. Statistical test interpretation. The results of a statistical hypothesis test must be interpreted for us to start making claims. This is a point that may beginners and experienced practitioners alike. There are two common forms that a result from a statistical hypothesis test may take, and they must be interpreted in different ways. They are the p-value and critical values. A statistical hypothesis test may return a value called p or the p-value. This is a quantity that we can use to interpret or quantify, either reject or fail to reject the null hypothesis. This is done by comparing the p-value to a threshold value chosen beforehand called the significance level. The significance level is often referred to by the Greek lowercase letter alphabet. A common value used for alpha is 5% or 0.05. A smaller alpha value suggests a more robust interpretation of the null hypothesis, such as 1% or 0.1%. The p-value is compared to the pre-chosen alpha value. A result is statistically significant when the p-value is less than alpha. This signifies a change was detected, that the default hypothesis can be rejected. Here is two conditions. If p-value greater than alpha fail to reject the null hypothesis, that is not significant result. The second one is if p-value less than and equals to alpha reject the null hypothesis, that is significant result. Reject versus failure to reject, the p-value is probabilistic. This means that when we interpret the result of a statistical test, we do not know what is true or false, only what is likely. Rejecting the null hypothesis means that there is sufficient statistical evidence that the null hypothesis does not look likely. Otherwise, it means that there is not sufficient statistical evidence to reject the null hypothesis. We may think about the statistical test in terms of the dichotomy of rejecting and accepting the null hypothesis. The danger is that if we say that we accept the null hypothesis, the language suggests that the null hypothesis is true. Instead, it is safer to say that we fail to reject the null hypothesis, as in there is insufficient statistical evidence to reject it. When reading reject versus fail to reject for the first time, it is confusing for beginners. You can think of it as reject versus accept in your mind. As long as you remind yourself that the result is probabilistic and that even an accepted null hypothesis still has a small probability of being wrong. Common p-value misinterpretations. This section highlights some common misinterpretation of the p-value in the result of statistical test. True or false null hypothesis, the interpretation of the p-value does not mean that the null hypothesis is true or false. It does mean that we have chosen to reject or fail to reject the null hypothesis at a specific statistical significance level. based on empirical evidence and the chosen statistical test, that is post hoc tuning. It doesn't mean that you can resample test until you achieve a desired result. It also does not mean that you can choose your p-value after you run the test. This is called p-hacking or hill climbing and will mean that the result you present will be fragile and not representative. In science, there is at best unethical and at worst fraud. Interpret critical values. Some tests does not return a p-value. Instead, they might return a list of critical values and their associated significance level, as well as a test statistics. These are usually non-parametric or distribution-free statistical hypothesis tests. The choice of returning a p-value or a list of critical values is really an implementation choice. The results are interpreted in a similar way instead of comparing a simple p-value to a pre-specified significance level. The test statistics is compared to the critical value at a chosen significance level. Here are 2 points. If test statistics less than critical value, fail to reject the null hypothesis. If test statistics greater than or equals to critical value, reject the null hypothesis. Again, the meaning of the result is similar in that the chosen significance level is a probabilistic decision on rejected or failed to reject the base assumption of the test given the data. Results are presented in the same way as with a p-value as either significance level or confidence level. The next one is normal distribution. Many continuous random variables have a bell-shaped or somewhat symmetric distribution. This is a normal distribution. In other words, we can say that the probability distribution of its relative frequency histogram follows a normal curve. The curve is bell-shaped, symmetric about the mean and defined by mu and s. That means the mean and standard deviation. There are normal curves for every combination of mean and standard deviation. The mean shifts the curve to the left or right. The standard deviation alters the spread of the curve. The first pair of curves have different means but the same standard deviation. The second pair of curves share the same mean but have different standard deviation. Here, the pink curve has a similar standard deviation. It is narrower and taller. And the probability is spread over a smaller range of values. The blue curve has a large standard deviation. The curve is flatter and the tails are thicker. The probability is spread over a large range of value properties of the normal curve. The mean is the center of that distribution and the highest point. The curve is symmetric about the mean. The total area under the curve is equal to 1. As x increase and decrease, the curve goes to 0 but never touches. A normal curve can be used to estimate probabilities. A normal curve can be used to estimate proportions of a population that have certain x values. The standard normal distribution, there are millions of possible combination of means and standard deviation, continuous random variables. Finding probabilities associated with these variables would require. To avoid this, we can rely on the standard normal distribution. The standard normal distribution is a special normal distribution with a mean is equals to 0 and standard deviation is equals to 1. We can use the z-score to standardize any normal random variable, converting the x value to z-scores, thus allowing us to use probabilities standard normal table. The standard normal table gives probabilities associated with specific Z scores. The negative side is for all Z score less than 0. The positive side is for all Z score greater than 0. Not all standard normal tables work the same way. The table we use is cumulative from the left, finding Z score for a given area. What if we have an area and we want to find the Z score associated with the area? Instead of Z score area, we want area Z score. We can use the standard normal table to find the area in the body of values and read backwards to find the associated Z score. Using the table, search the probabilities to find an area that is closest to the probability you are interested in. To find a Z score for which the area to the right is 5%, since the table is cumulative from the left, you must use the complement of 5%, that is 1 minus 0.05, that is equals to 0.9500. Area in between two Z scores to find Z score that limit the middle 95%. The middle 95% has 2.5% on the right and 2.5% on the left. Use the symmetry of the curve. Look at your standard normal table. Since the table is cumulative from the left, it is easier to find the area to the left first. Find the area of 0.025 on the negative side of the table. The Z score for the area to the left is minus 1.96. Since the curve is symmetric, the Z score for the area to the right is 1.96. Common Z score, there are many commonly used Z scores. Z.025 is equals to 1.96 and the area between minus 1.96 and 1.96 is 95%. Z.005 is equals to 2.575 and the area between minus 2.575 and 2.575 is 99%. Applications of the normal distribution. Typically, our normally distributed data do not have mean is equals to 0 and standard deviation is equals to 0. But we can relate any normal distribution to the standard normal distribution using the Z score. We can transform values of X to value of Z. Adult year population weights are normally distributed with mean is equals to 110 lb and S is equals to 29.7 lb. As a biologist, you determine that a weight less than 82 lb is unhealthy and you want to know what proportion of your population is unhealthy. That is, probability X is less than 82. Convert 82 to a Z score. The X value of 82 is 0.94 standard deviations below the mean. Go to the standard normal table and find the area associated with a Z score of 0.94. This is an area to the left problem, so you can read directly from the table to get the probability. P X is less than 82 is equals to 0.736, approximately 17.36% of the population of adult deer is underweight. Or one deer chosen at random will have a 17.36% change of a weighting less than 82 lb. Next one is T distribution. In probability and statistics, the T distribution is any member of a family of continuous probability distribution that arise when estimating the mean of a normally distributed population in situations where the sample size is small and population standard deviation is unknown. According to the central limit theorem, the sampling distribution of a statistics will follow a normal distribution as long as the sample size is sufficiently large. Therefore, when we know the standard deviation of the population, we can compute a z-score and use the normal distribution to evaluate probabilistic with the sample mean. Center limit theorem. According to the center limit theorem, the mean of a sample of data will be closer to the mean of the overall population in question. As the sample size increase, notwithstanding the actual distribution of the data, in the other word we can say that the data is accurate whether the distribution is normal. As a general rule, sample size equal to or greater than 30 or deemed sufficient for the CLT to hold, meaning that the distribution of the sample mean is fairly normally distributed. Therefore, the more samples one takes, the more the graph result take the shape of normal distribution. Andrew limit distribution exhibits a phenomenon where the average of the sample means and the standard deviation equal the population mean, and standard deviation, which is extremely used in accurately predicting the characteristics of population. For the random samples we take from the population, we can compute the mean of the sample means. And the standard deviation of the sample mean is this. Center limit theorem will a normal population. The figure illustrates a normal distribution characteristics acts in a population in which the population mean is 75 with a standard deviation of 8. If we take simple random samples of size n is equals to 10 from the population and compute the mean for each of the samples, the distribution of a sample mean should be approximately normal according to the central limit theorem. Note that the sample size n is equals to 10 is less than 30, but the source population is normally distributed. So this is not a problem. The distribution of the sample mean is illustrated here. Note that the horizontal axis is different from the previous illustration and that the range is narrower. The mean of the sample means is 75 and the standard deviation of the sample mean is 2.5. With the standard deviation of the sample means compute as follows. If we were to take sample of n is equals to 5, instead of n is equals to 10, we would get a similar distribution, but the variation among the sample means would be larger. In fact, when we deal this, we got a sample mean of 75 and a sample standard deviation that is 3.6. The next one is confidence intervals. Statisticians can use a confidence interval to describe the normal amount of uncertainty associated with a simple estimate of a population parameter. How to interpret confidence intervals? Suppose that a 90% confidence interval states that the population mean is greater than 100 and less than 200. How would you interpret this statement? Some people think this means there is a 90% chance that the population mean falls between 100 and 200. This is incorrect. Like any population parameter, the population mean is a constant, not a random variable. It does not change. The probability that a constant falls within any given range is always 0.00 or 1.00. Confidence interval data requires to express a confidence interval, you need three pieces of information: confidence level, statistics, margin of error. Given these inputs, the range of the confidence interval is defined by the sample statistics plus margin of error. And the uncertainty associated with the confidence interval is specified by the confidence level. Often the margin of error is not given. You must calculate it. Previously we described how to compute the margin of error. Construct a confidence interval. There are 4 steps to constructing a confidence interval. Identify a sample statistics. Choose the statistic that you will use to estimate a population parameter. Select a confidence level. As we noted in the previous session, the confidence level describes the uncertainty of a sampling method. Often researchers choose 90%, 95% or 99% confidence levels, but any percentage can be used. Find the margin of error. If you are working on a homework problem or a test question, the margin of error may be given. Often, however, you will need to compute the margin of error based on one of the following question, that is, margin of error is equals to critical value. Standard deviation of statistical margin of error is equals to critical value standard error of statistics. Regression analysis or linear regression. Linear regression is usually among the first few topics which people pick while learning predictive modeling. In this technique, the dependent variable is continuous independent variable. Can be continuous or discrete, and nature of regression line is linear. Linear regression establishes a relationship between dependent variable y and one or more independent variable x using a best fit straight line. It is represented by an equation, that is y is equals to a plus b multiplied by x plus e, where a is intercept, b is slope of the line and e is error term. This equation can be used to predict the value of target variable based on given predictor variable, obtain best fit line. This task can be easily accomplished by least square method. It is the most common method used for fitting a regression line. It calculates the best fit line for the observed data by minimizing the sum of the squares of the vertical deviations from each data point of the line. Because the deviations are first squared, when added, there is a no cancelling out between positive and negative values. Next one is probability distribution. Recall that a random variable is a variable whose value is the outcome of a random event. For example, a random variable could be the outcome of the roll of a die or the flip of a coin. A probability distribution is a list of all of the possible outcomes of a random variable along with their corresponding probability values. To give a concrete example, here is the probability distribution of a fair 6-sided die. The probability distribution for a fair 6-sided device, to be explicit, there is an example of a distinct univariate probability distribution with finite support.